Good morning, everybody. Don't forget before we start this lecture that this lecture and all my lectures are brought to you by the good makers of Sunshine Pills. With Sunshine Pills, every day is a bluebird day. And Sunshine Pills are produced, as I mentioned, by the good people from Capybara Pharmaceuticals. So thank you very much. And don't forget our sponsors. And if you're feeling ill in any way, Sunshine Pills will help you get out of the doldrums and into the good. And we need to be good when we're doing data analysis and statistics, or we're talking about different research methods. And today we're going to be talking about developing a measure. Okay, so there's a lot of definitions here, so bear with me. I'm trying to, when I was writing this chapter, I was looking at all these different terms. We measure, survey. There's so many different things that we use. Assessments, tests, try to clarify this in my mind was more important than clarifying it in your mind, because how could I clarify it in your mind if I needed to clarify it in mine? So let's start with measures. So researchers we know employ measures to assess critical concepts, and in this case I'm discussing psychology, but it could be in any field as well. So measures are designed to assess very specific concepts, something like social anxiety, depressive symptoms. You could get a measure to assess that concept. Concepts are these cognitive abstractions. They are these entities that cannot be measured directly. Oh, okay, so we need some way to measure them. When we design these measures, we operationalize our concepts into what are known as constructs. Okay, so we translate something that's abstract into something that's measurable. So you'll hear terms constructs used a lot, but remember they're these operationalized concepts. So that's when you constructed something, in other words, to measure a concept. Ideally, when we're dealing with these tools, these instruments, we should have one measure for one concept. And some examples are the CESD, the Center for Epidemiological Studies, depression. So this is a measure that measures depression, or depressive symptoms, actually, symptoms of depression. The PHILMS, which is the Philadelphia Mindfulness Scale, brought to you by your one of your professors. You see a nice little spider crawling down. Nature is beautiful, isn't it? Yeah, Leah Cardassiato is the professor who developed the PHILMS. Sometimes there can be multiple concepts underlying a measure. Like, for instance, with the CESD, often people treat it as a single concept, like, oh, it measures depressive symptoms, but previous research has shown that there are multiple concepts underlying the overall concept of depressive symptoms. And those include depressive affect, positive affect, somatic symptoms, and interpersonal distress. So those would be four sub-concepts, or you can even say constructs, as they're measures, four constructs underlying the overall depressive symptoms construct that's supposedly measured by the CESD. So this is just something that we're going to get back to that shortly, but something for you to think about. A survey is a package containing a variety of different measures. Aha. So from it, they may include demographics, like race, ethnicity, income, education. They may include multiple measures, maybe a measure of depressive symptoms, maybe one of anxiety, maybe one of eating habits or something like that. A survey can be designed without a specific study in mind, and examples of these include the behavioral risk factor surveillance system that's run by the CDC, Center for Epidemiological, by the CDC, Center for Disease Control and Prevention. Yeah, I'm all over the place today. The YRBSS, the Youth Risk Behavior Surveillance System, also operated by the CDC. So these studies are ongoing to collect data, but without any specific study in mind. So they're just more like, let's collect data. I should call them data collections, perhaps, rather than studies. I use them when I have an interesting research question in mind. I can collect the data because there's a bunch of general questions there, and I can answer many of my research questions. Surveying is the process of administering a survey. So for instance, when say the YRBSS goes to a high school and starts administering surveys to adolescents, that's surveying, entering and cleaning the survey data. Cleaning means, we take a toothbrush and put some soap on it and start cleaning the, wait, no, that's wrong, sorry. No, cleaning data means you go look through the data, make sure there are no errors, and deal with issues that might be important, like dealing with missing data. What do you do with that? Maybe redefining or creating variables. And then there's also data analysis. So all of these fall underneath the surveying function. A questionnaire is a set of items designed to answer a specific research question or a set of hypotheses. So survey and questionnaire can be used interchangeably. So I'm not so worried about that. I'm not going to start going around collecting people. Hi, you're not doing a survey, you're actually doing a questionnaire. They are generally designed for a particular study. So for instance, one study that I worked with was known as AVATAR, and I can't remember what that acronym stands for, but it sounds cool, right? It was a questionnaire, and it had many different measures within it, but it was designed for whatever the hypotheses were of that study. Tests are similar to questionnaires. They're designed to assess specific concepts, and they're used to compare scores for individuals to a population, right? Like the IQ test, the SAT, and all the GRE, those are all tests, and they're always used to make comparisons. All right, so that gives you some indication of the complexity of this topic and why it can be very confusing. And sometimes it's really hard to figure out what label should I use for what I'm doing. So hopefully you can use this as a roadmap, okay, to help you deal with those situations. Talk about the development of a measurement or the whole process there. I wrote like a good article on this. It was actually more of a chapter for a book on how to why you shouldn't create a new measure. And I've done it myself. I did it for my dissertation. I've done it many different times. It's an interesting process. Interesting process. So first step, and I like doing steps because people like steps, right? Except for when they're climbing them. Now they like steps so they can have like a guideline. What should I do next? What's the first thing I should do? First, make sure the measure is indeed necessary. So you explore the literature for other measures of the concept. You compare and contrast the proposed measure to the existing measure. You only construct a new measure if there are flaws in the existing measure or if no measure exists. So that should be number one, because this is a painful process. So why do you want to inflict pain on yourself if you don't need to? And step number two, generate a set of, so let's assuming now that this measure is indeed useful. So we're going to generate a set of items to assess the concept of interest. We want to make sure the items don't overlap so that they're different. The item should assess an indicator of the concept, all indicators of the concept. And we'll talk more about that. Be mindful of the prototypical respondent. Who's your respondent, right? When you're writing them. So you can't write them in a way that people won't understand. Indeed, items should be accessible to an individual with at least a 6th grade education, but that means you're not going to be using jargon that is not accessible to everybody. Also, you don't want to have too many items as you're generating items, because too many items result in fatigue, and they could result in what are known as response sets. So maybe you've done this yourself when you're filling out a long measure and you're getting tired, so you just like you go straight down, all ones or something like that, because I'm just too tired. And that's problematic because sometimes items are reverse scored. Like one item could say, I love myself, and the next item could say, I hate myself. So a 1 on each of those wouldn't be equivalent. I use an example here of a measure that I've been working on it, as you know, or if you don't, I work with skiing. I am a ski instructor. I coach and created our ski club sports ski team at LaSalle. So, I was thinking that it would be really good to have a measure of skiing because now there's these awesome tools that we could use to validate it. So this is a prototypical questionnaire. I have 31 items in here. I think this is a lot. So I'm hopefully going to whittle it down to fewer, because usually when we're conducting a study and we're using a questionnaire, the questionnaire will have more than one measure. So if this is one measure, it already has 31 items in it, right? So I may want to ask something like, I may want to have my respondents complete a measure on depression, like say the CESD, which has 20 items. So now you have 51 items. People get tired after a while, right? So fatigue is problematic, and we don't want that to happen. Step 3, have others assess the utility of the items. So experts in the field. So even though I teach skiing, there are people who are better at it than I am, who have higher credentials than I do. So I had some of my colleagues, including people who are testers for our governing body, look at it and give me feedback. And other people who are experts on survey design as well. I had people look at that. So that you want to have those people look at it, and then based on their feedback, you might need to refine some of the items. Step number 4. Step number 5, define the measurement scale. A lot of you probably have heard of Likert, not Likert, Likert scales. Those scales are used when respondents are asked to endorse their level of agreement with a statement, from strongly disagree to strongly agree. Or you could have some variation of those, I call Likert type scales. And in fact, when I'm writing a paper, I will actually define the scale based on Likert or Likert type. So Likert type scale may use 2 other poles rather than strongly agree and strongly disagree, like really true for me or not true for me at all, something like that. But it's basically the same thing. I've never used a semantic differential scale, but many people do. So obviously I'm going to discuss them. The respondent rates a statement, a characteristic, a profession using 2 opposite poles. So here's an example. Rate how interpersonal relationships with fellow graduate students make you feel on the following dimension, marking your feeling with a tick mark. So for instance, in terms of love and hate, if you really hate all of your peers, you probably put a line like maybe right here, pleasant to unpleasant. If most of your interactions are, somewhere in between, you probably put a tick mark here. If other students make you happy, you probably put a tick mark over here, right? So this is just another type of measurement scale. It's not too different from the Likert type scale. Sometimes individuals use numbers, rulers, or characters to indicate the level of agreement. For instance, in my skiing self-perception profile, I use numbers, right? And this is a Likert type scale, right? Because you have not at all true for me versus very true for me. I think one of the feedback I had was get rid of the does not apply to me. So I'll probably get rid of that. So here you would mark whatever number you have. And these are actually discrete categories. They're going from lower to higher. So this is an ordinal type scale. Some people argue that if you have 6 levels, you can treat an ordinal scale like a continuous scale. So maybe I can add another one here to do that, but that's arguable. One of the things we want is, if possible, for our scales to be continuous. So a continuous variable, well, is a variable that's has a continuum that goes from whatever 0 to some other number. And you can have these markings represent any value on that scale, right? One way, instead of using discrete values like I did in the skiing self-perception profile, what I could do is something similar to what was done here, the semantic differential scale. I could just have a ruler that indicates how strongly one agrees with the statement, and then people can mark it. And what we can do is we can measure the distance between the lowest and the highest. I can actually take out a ruler and measure it and say, so this is what person's score is. Some believe that that's much more accurate, right? And sometimes when you're in a physician's office, you'll see characters used to provide feedback. So it's another type of scale. Like for instance, if you've ever been asked about your pain and you look on your healthcare provider's door, there might be like a poster showing, smiley face for no pain at all. And then there's this crying for severe pain. So there's different ways we can rate our agreement with different statements or our responses to questions. Step number 6 is to conduct a pilot study. So this is a study in which we collect a small amount of data and we just get some information from it. Like we might be asking, are the items easy to understand, right? If a lot of people give me feedback, well, the items were okay, but I didn't really get most of them. That's not good. Is the measure too long? So we can understand whether or not people feel fatigue. Are there any items that don't belong? So again, so this is similar to giving our measure to the experts, our items to the experts. We're going to probably refine if necessary. One of my measures called the SIMS, the subjective importance of smoking measure, underwent several revisions after the pilot studies. And I kept revising, and we had 2 different pilot studies for it, and I was learning with which population the measure works and where it doesn't work. So I had to eliminate some items. And then finally, you conduct a larger study to assess the factor structure of the measure. So this is something we call the internal structure analysis. I'll talk about that in a second. We're going to need a large sample. Sample size is really difficult to determine. There are all these heuristics, like 5 individuals per item. So 10 items, that'll be 50. Some people say 10 participants per item. Some people use round number of, say, 100 participants is good. It's really hard to say. There is no, unfortunately, a way to use G-power to ask for a sample size or to calculate your sample size. There are ways to do that. You could do what's known as a Monte Carlo analysis, where you simulate data and you can come up with the numbers. So there are ways of doing it. And if I were doing this as a study, I'd probably use Monte Carlo method to estimate the sample size. Also, your sample should be representative of the population to which the researcher is interested in generalizing the findings. That should always be the case anyway. Doesn't matter which type of sampling you use, it's highly unlikely that most people will get a random sample. Although there are these different tools now that people can use for surveying, whether it's SurveyMonkey or something like that, where people will go out and collect the data for you and help you get everything. So maybe the sampling is better there than it would be if I just went out and started recruiting people, because I don't have the capacity to do that large random sampling. I don't know the sampling frame, right? I don't know that. So I mentioned earlier that we have to assess the internal and the internal factor structure, but also the external factor structure. So let's talk about the internal factor structure. Internal structure, not factor structure. To do that, we use something called an exploratory factor analysis. There's actually 2 types of factor analysis. There's exploratory and confirmatory. When we're trying to understand the nature of our measure, we start with an exploratory factor analysis, unless we already have a good idea, and then we can go to a confirmatory, and we'd want to confirm it. So factor analysis is a method that is used to try to identify how many latent variables. So a factor is a latent variable. So a variable that's not measured or not measurable directly, right? So for instance, something like intelligence, impulsivity, and anxiety, those are latent. They're not directly measurable. You might say, but wait a minute, I can measure intelligence by an intelligence test, or I can measure anxiety by, I don't know, looking at people's pupil dilation, right? Well, those are indicators of these latent variables. And yes, those indicators are good. And indeed, those are what we use to define our latent variables. So this is a typical exploratory factor analysis model, where you have 3 different latent variables. You'll notice that we use circles or ovals to represent latent variables, and we use squares to represent measured variables. So for instance, for intelligence, I might find 3 items that are really, really good indicators of intelligence. and I can use those to indicate intelligence. So those are indicators of intelligence because I can't measure intelligence directly. And I can't measure impulsivity directly. I have to look for indicators of impulsivity, like fidgety or unable to complete a task that requires more than 1 minute of time, etc. So this is your prototypical factor analysis. I'll talk about this other stuff in a second. It has its roots in the work of Charles Spearman. Charles Spearman proposed that there is a general intelligence G factor that is responsible for how students perform on school tasks. So there, in his model, there was one factor, there wouldn't have been three, right? And that's responsible for the way you respond on any item related to intelligence or any academic type item. What's really cool about this, and as you're learning this, you're thinking that I'm talking about latent or factors, latent variables or factors, but what you should be thinking about is what the heck is this thing? Is there such a thing that exists in my head that has no density, nothing like that, but it's there, right? And it's how, I mean, what is it, like some connection of neurons or a particular firing pattern for my neurons that create impulsivity or something like that? That's what always fascinated me. Yeah. So this G factor, by the way, I'll talk about these other little ones here. You'll notice that there's other little circles underneath, and these we can call error or uniqueness. So each of these, the responses to each of these items here will have some unique portion of the variance that's accounted for just by that, whatever that item is itself, right? So while intelligence might account for, say, 70% of why you answered the way you did on V9, 25% is, so that's not, say 25% is accounted for by something that's unique to that item itself. So that's 95%. And then there's another 5% that could be due to measurement error, like maybe something happened when you were answering it, just some stupid stuff that could happen. So this is more what we just overall call the error variance. And we usually we try to account for as much of the variability using our factor and try to minimize the error variance. But you have to account for it because it'll always be there. Okay, we talked about that. Bubba talked about that. See, I really sometimes just I scoop myself or go beyond what I'm putting in the notes. Okay, so with EFA though, how does it work? And you don't need to know how to do it unless you're creating a measure, or if you're analyzing data. A rule is that you should always conduct an EFA or CFA when you're using a new data set, because as you know from last week, we talked about the sampling distribution. Each sample can be very, very unique. And if a prior exploratory factor analysis was done on one sample, it may or may not apply to your sample, right? So you should always redo this. When I learned how to do research when I was doing my doctorate, that's what we did. It said you have to do the EFA or confirmatory factor analysis every single time you collect new data. You have no idea if the measure will apply to your participants, given its structure. So one of the first steps is to determine how many factors underlie the measured variable. So again, here's an example. We had 9 measured variables and we had 3 factors, but how did we come up with 3? So that's the first step. And we have 2 different methods we use, and both of these are involving something known as eigenvalues. And eigenvalues are estimations of the variance accounted for by a factor. And each of those circles that we had, or those ovals, were factors. And if you'll notice one thing about these, the arrows point from the factor to the measured variable, right? So that means that in a sense, we're proposing a causation here. I'm not saying it is causal, but we're proposing causation. In other words, this factor anxious is responsible for the relations among these 3 variables here. So see, they're related to one another, and this impulsivity has no bearing on them, right? No direct bearing on them. There's no arrows going from impulsivity. However, there's these 2-headed arrows indicating that anxiety and impulsivity are correlated, right? and impulsivity and intelligence are correlated. I probably could have had another one from intelligence to anxiety, right, to make sure that they're correlated. So there is some way to trace the relation among, say, variable V1 and variable V7, right, through these complicated pathways here, compound arrows, if you will. But what I'm looking for is the how many factors underlie these different items here. And to do that, we have to come up with some kind of a criterion. Oh, and also because the arrows are pointing to the measured variables, we can calculate the proportion of variance that's accounted for by that factor, as well as the proportion of variance that's accounted for by those things I call the errors. One criterion is known as the Kaiser criterion. So we select the number of factors with eigenvalues greater than 1. So the eigenvalues, again, are representing the variance accounted for by each one of those factors. So you'll get, it's interesting, you'll get as many factors in your output if you're running this in a statistical package. You'll get as many factors in your output as there are items. So if I have 9 items, I would get 9 factors. However, to determine how many factors there are, I'll look at the eigenvalues, and each of these eigenvalues will represent some proportion of the variance. So if let's say the first eigenvalue is 5, and I have 10 items, that means that first component, that first factor, accounts for 50% of the variance. Right? Eigenvalue equal 5 divided by 10 items, it's 0.5, right? So 50% of the variance. So this criterion says we'll look at all the eigenvalues greater than or equal to 1, and we'll use that to indicate the number of factors. And if we add together all the eigenvalues, they will equal the number of items. So when should we use this criterion? Because I mentioned there's more than one. Well, according to Patuch, Stevens, the Kaiser criterion is best when either the sample size is greater than or equal to 250, or the commonalities are above 0.6, 6.6, like 60%, or if the number of variables is less than 30, no, this is sample size n variables, right? And you can have like a large number of variables, and the commonalities are above 0.7. So what are commonalities? They are the squared factor loadings. The loadings are the correlations between each item and the factor. And you'll see that when you're looking at a factor analysis. You'll get the loadings, you get the commonalities. So the commonalities are akin to an R-square in multiple correlation. Yeah, so you're going to get for each item what proportion of the variance was accounted for by the different factors. Interesting stuff, huh? You think, well, what do I need to know of this? This is a research methods class. Well, you're reading a lot of stuff that uses these different measures, right? And whenever people report the measures, the one thing that they always report, and I'll get to this in a moment, is the Cronbach's coefficient alpha. More rarely do they discuss the factor analysis results, but they should. And when they do, you should be able to interpret them. Well, okay, so how did you arrive at that number of factors? What was your criterion? Did you use Kaiser? So now you know what that means. And when they say we use the Kaiser criterion, you'll have an idea of what is discussed. And you might be able to argue against why they picked so few or so many factors. A second criterion is something known as a scree plot. It's a plot. It's a plot of the eigenvalues on the y-axis and the items on the x-axis. So here's a figure of a scree plot. There you go. So basically, these are the eigenvalues. So the first one was pretty high up. There was like 8 to 8.5. The second one was around 1. So in this case, using Kaiser, we'd probably just pick 1, right? Because this looks like this other eigenvalue is a little bit below 1. Scree criteria tells you to pick the number of factors before the elbow. So here's a really clear elbow, right? There's an elbow in this graph. And there's only one factor before the elbow. The second one is at the elbow, so that doesn't count. So it's the first one. So Patuch and Stevens recommend we use the scree plot when the sample size is greater than 200 And most commonalities are large. So you want it to be large, whatever large means in that case. So here, I'll just give you an example of something I was doing today as I was prepping for our lecture. I pulled several items that are really, they don't belong together at all. Body mass and index, CSD, self-esteem, and perceived physical appearance. And I just ran quick exploratory factor analysis. And here I have one, using the Kaiser criterion, I have one eigenvalue, 2.193. That's above one. So this would tell me that I have one factor. This other one is kind of close, but it's not close. Close is only good. What is it, horseshoes and darts or something? I have no idea. And it shows you the proportion of the variance, like 2.193 divided by 4, you get 54.827%. Right? And then here's the scree plot. You can see that there's a less pronounced elbow, but there still is an elbow here. So you should still go with the one factor. Some people could argue, well, it's not enough of an elbow. You can make, that's what's fun about this. It's science, but it's also, there's some subjectivity involved here, right? Here's our component matrix. This is the correlation between each item and the factor. Some are negative and some are positive. Interesting stuff. So how do we interpret the factor loadings? Well, what we do then is we take a look at the loadings, right? And we take those loadings that we consider strong. Generally, we call strong around 0.4. And I use the absolute value sign to indicate that we're not as interested in the negative. I mean, negative is important as we're defining, we're defining our factors, and we're giving them names. So we have to give names to factors. But here's an example for my Sims measure. This had to do with subjective importance of smoking. Like there's items like cigarettes help me get through hard times, smoking helps me meet new people, et cetera, et cetera. I'm looking at the correlation with each factor, right? And so this one is very, very low. However, if we look at factor 2, this correlation is much stronger, 0.588. And then I look at, let's see, smoking helps me meet new people. Factor 3 has a loading of 0.482, which is above 0.4, so that meets my criterion. So this one is more likely to load on factor 3. I cannot cope without cigarettes. This item it's kind of close here, right? Factor 1 and factor 2, but if we use the 0.4 cutoff, we'd go with factor 2, etc. Some are really strongly related to a given factor, like smoking is a big part of who I am. Its loading was 0.896, so that's clearly belongs to factor 1, right? So what we do then is we take the pattern of loadings, like for instance, cigarettes are a big part of my identity. I cannot see myself not smoking. These all have high factor loading. So this factor probably could be considered identity. So if I wish to label it, I would label it as identity if I were to use this solution. Okay. Let's see. Okay, cool. So after, what do we do after we've completed our EFA? The next step would be to start all over again from scratch with a new sample. Or in some cases, you can take if you have a really big sample, like you have 1,000 people, you can randomize it so you get half in the first study and half in the second. But you redo this, instead of using exploratory factor analysis, you use something called confirmatory factor analysis, CFA. So the difference between EFA and CFA is with CFA, you propose the factor structure and then you test that factor structure. So this is something known as, we use something called structural equation modeling. So a CFA is an SEM. SEM stands for structural equation modeling. And in this method, what we do is we test the fit of our data to the data proposed by the CFA. So believe it or not, I can take a matrix. So a matrix is, it's like if I think of it, it's a row. Matrix has rows and columns. So it's a set of numbers that fit into a certain number of rows and columns. usually we define the size of a matrix as the number of row times the number of columns. So let's say I have let's say we're creating a factor structure for a factor analysis for 4 different items. So we have 4 items, and we want to see if they fit whatever the factor structure proposed by the EFA. Say the EFA suggests that there's one factor underlying these 4 items, so our CFA should validate that. So we create this matrix with all the variances of those 4 variables running down the diagonal of that matrix. And then the off-diagonal elements would be the covariances. So covariances are another way of doing correlations, but they're not standardized. But anyway, that initial set of data is my input, and then I put in my model, and using that model, I can actually recreate a variance and covariance matrix. I actually, in my new textbook, in my new stats textbook, I actually give an example of how this is done, mathematically speaking. Once we have the recreated variance covariance matrix based on my model, I can compare it entry by entry to my original variance covariance matrix, and we can test how well the two fit together. So that's what we're doing here. We're using something known as a chi-square test of model fit. We'd like the two to not differ at all. Like, so my null hypothesis in this case would be that the variance and covariance based on my model is equal to the variance and covariance, the original data variance covariance matrix. The alternative is that they're not equal. So in this case, we would love to fail to reject the null hypothesis, and we say that the two are equal. So that's like the ideal way to test whether or not our model fits the data well. So that's what we're saying. Does our model fit the data well? Does this CFA model fit the data well? Because this is the CFA that's based on the original study, right? We use that chi-square test. But one of the problems with the chi-square test, and this is very arguable, okay? A lot of people debate this all the time, but one of its problems is it's highly sensitive to sample size. The larger the sample size, the more likely you'll find a significant difference. So other indicators of fit have been created or have been developed, like the comparative fit index, the RMSEA, the root mean square error of approximation. And there's certain criteria for what we consider a good fitting model, like a model that has a CFI of 0.95 or greater is considered good, and largest value is 1, and with RMSEA, a value of less than or equal to 0.08. Some people say 0.05, and they give you different degrees of fit as you go down closer to 0. So these are interesting indicators of fit. What differentiates them from the chi-square is they take into account model complexity. So you're punished if your model is extremely complex using these methods. There's also this third method that I use for my SIMS paper. It's called exploratory structural equation modeling. You know, those good scientists, they never stop coming up with different methods to do research. And in this case, the ESEM method, it kind of combines both exploratory and confirmatory into a single model. And it's really, really cool. So you don't need to collect data for 2 different studies. And I'd mentioned before that the whole measurement design process is really pain in the rear, because you have to go through so many different steps and do so much work. It's not really worth it, especially if you're in a career where you need a lot of publications to advance, like from, say, associate to full professor or whatever. So those aren't necessarily worth doing, but for a graduate student, it's probably not that bad, because, you know, a graduate student, you have to do this major study, right, to get your diploma, right? So I like this method because it allows you to use both. So it's called ESEM, exploratory structural equation modeling. If you're interested in that, you can look at my paper on the SIMS. This, by the way, this is your prototypical EFA model. It doesn't look any different than the model I showed you earlier for the exploratory factor analysis. The only difference here is that you are proposing the model in advance. I'll tell you one thing that that is different. When you do an EFA, you'll have basically an arrow from the factors to every single item. Just some of these arrows will be more, some of the factor loadings will be stronger than others. And we saw that actually here, where we're looking at this. So this is an item and this is factor one. You'll notice how factor one has a loading on every single item. Some of them are not that good, but some of them are very good. So what you see with the CFA is the CFA doesn't have that same thing, especially like this model that I showed here is actually not an EFA model, it's a CFA model, right? It's a confirmatory factor analysis model. And this is very prototypical of a CFA model. You see that there's no arrows for anxiety to item 4, 5, 6, 7, 8, and 9. So it's assuming that those paths have a 0 value to them, right? They're 0. Same from impulsivity to items 1, 2, 3, 7, 8, and 9. Why are all the other numbers afraid of 7? Because 7, 8, 9. I'm sorry, I can't help it every time I see that. So that's dad jokes. Is that what they call those? So the problem with CFA is it has that one issue where it constrains certain values to 0, and ESEM doesn't do that. So ESEM, you have all the factor loadings are estimated. So you get a really interesting model, and you get all the fit statistics, which you don't get in EFA, but you do get in CFA. So it's a really interesting method. And again, I used it before. Let's talk about reliability. So reliability is a measure of internal consistency. I mean, there's other ways to discuss reliability. Reliability means you can count on something, right? You can have a bathroom scale that's reliable. It gives you pretty much the same weight, within a few pounds based on what you ate in a given day from day to day, right? That's considered reliable, right? But that's not what the kind of reliability I'm talking about here. I'm talking about reliability as internal consistency among the items. This measure of alpha, or Cronbach's coefficient alpha, is often the only thing that's reported by people in a study, and I have no idea why they put so much weight on it. It's only one thing. It doesn't talk about the validity, whether or not a measure measures what it was designed to measure. It just talks about internal consistency. Geez. Well, we would, if we did a factor analysis and came up with, say, 3 or 4 factors, we should do an alpha for each one of those factors. We're certainly going to do it for anything that we're going to use in a study. Like if one of our latent variables is something that we're going to add up all the indicators and create a measure, yeah, we should do an alpha, right? So, or if you have just a single alpha for a measure, like I mentioned the CESD, some people use the CESD by just adding all the 20 items together rather than breaking them down into the 4 different factors. And in that case, they should provide an alpha for those 20 items. The heuristics are 0.7, suggests a good reliability. Reliability is affected by the number of items. So in this is the equation for Cronbach's coefficient alpha. K is the number of items. And then we have V is variance of each item, and then VT is the total variance, which these two, if you add these together, they're not going to equal the total variance unless the variables are independent of one another, because you have to account for the correlation between them. The thing is that the larger the number of items, the higher the Cronbach's coefficient alpha. It's probably due to the variances, how variance is affected by having more items. I mean, if you just plugged in, I was doing this for fun today. I was just plugging in values here. Okay, so here's there's 11 items, and let's see, what did I do here? Oh, because that equation has K, and then it has K minus 1. They're multiplied together, right? And then you get there, and then then we divide. So you divided K by K minus 1, and then you multiply this by the variance. That second part of the equation here in parentheses, and I say, well, what happens? Is it just it's obviously not just the items when you look at this, when you look at how many items we have, it's not just the items, because we just increased the number of items our numerator actually, or not, the first element shrinks, right? Starts shrinking, so it's not going to be increasing our alpha. However, if our variance changes, like the proportion of the variance accounted for by the different items, if that changes, or the relation, excuse me, I shouldn't say proportion of variance, but here, so there's a quotient here, right? The sum of the individual variances divided by the total variance. If this changes, this would actually impact your alpha. But the bottom line is the larger number of items you have, the higher your alpha. So a lot of times when people are reviewing manuscripts, when somebody reports a very high alpha, the yeah, but people, those are my favorite people, the ones who say yeah, but to everything. They'll say, yeah, but you had a lot of items. Well, you kind of can see what happens. It really affects the variability of the measurement of the measure. But that's to me, that's not that consequential. I'd look more at things like the validity of the measure. And then this is okay, that's an interesting item, and that has something to say about the internal consistency, but give me more information about the entire measure. When we're designing measure, we also do what's known, so that was an internal structure analysis when we look at the factors, do the factor analysis, and then we also look at the Cronbach's coefficient alpha. The second part, what we want to do is we want to look at the cross-structure analysis. So we want to compare our measure to other measures. Validity, as I noted earlier, is the ability of an instrument to measure what it was designed to measure. So if a bathroom scale should measure weight, not height, it'd be valid if it measures weight, not if it measures height. To assess the validity of a measure, we usually use some kind of a criterion. So if I was using a bathroom scale and I have a 50-pound weight, like a dumbbell or a kettlebell that weighs 50 pounds, and I stick it on the scale, it should read 50 pounds. Although more newer scales now are much more complicated than the older ones, and they work in different ways. So, but in general, you'd have to have some kind of criterion. So that's the perfect criterion. But for a lot of the things that we measure, like self-esteem, there is no criterion. So it becomes much more complicated. But we use things that are supposedly related, like self-esteem should be related to happiness or something like that. So we could use that sort of as a criterion. And what we use those criterion or criterion-like measures to assess the convergent validity of a measure. So our item should be strongly related to similar or more strongly related to similar concepts than it would be to divergent concepts, right? So for instance, a measure of weight should be more strongly related to weight than it should be to, I don't know, one's happiness, right? Because those are two separate measures. So generally, when people report about their measures, they should report both convergent and discriminant validity. And usually they'll compare them. So convergent validity should be stronger than discriminant validity, or divergent validity, I should say, divergent validity. So your measure should be more strongly related to similar measures than to opposite items or dissimilar measures. We can also measure predictive validity. How well does our measure predict something that it should predict? So with my SIMS measure, I used smoking abstinence as a criterion for predictive validity. In theory, if smoking is important, and the SIMS was looking at how important smoking was to an individual, those people who think smoking is important are less likely to abstain, right? They're more likely to smoke than people who think cigarettes are not that important to them. So that's what we ended up finding, actually. So that was good. That was a good measure of predictive validity. And another example is something like positive predictive validity that has predictive validity in the title. We use this a lot in medical research, like does a medical test predict disease status? So if it doesn't, is it worth testing? Like for instance, when you screen for something like colon cancer, if the predictive validity is very low, is it worth screening? Or when we screen for COVID, if the predictive validity is low, should we be screening? What is high predictive validity? Well, I'd say probability of having the disease given you test positive should be close to 1, right? Not 0.5 or 0.3 or 0.2 or whatever it is. That, my friends, is the end of this lecture. And don't forget, this lecture was brought to you by the fine people at Happy Bar Pharmaceuticals and their beautiful product, Sunshine Pills, where every day is a Bluebird Day, Sunshine Pills. Thank you and have a wonderful day.